Welcome to this video tutorial on graphing logarithmic functions by hand. We are going to look at two graphs, come up with what they are, and see if you can graph them as well. Perhaps you want to hit pause and try it out before we proceed together. On this first one, what we are going to do is invoke the properties of logarithms right off the bat. So notice it's log base 6. We're going to try to write things in terms of a 6. 216 is 6 cubed. And we're going to convert the square root into an exponent, so that's going to be x minus 5 to the 1/2 power. Now with properties of logs, the log of a quotient is the difference of the two logs. So we're going to split the log of the quotient into the difference of the two logs. Then don't forget that the exponent can come out front, so this will be 3 log base 6 of 6 minus 1/2, again because the exponent comes out front, log base 6 of x minus 5. When we simplify, the log base 6 of 6 is 1 because 6 to the first power is equal to 6. So as we simplify this, we can rewrite it as negative 1/2 log base 6 of x minus 5 plus 3. That's the form that's most helpful to sketch a graph of this function by hand, because now we can write out its transformations. It reflects across the x, has a vertical stretch of 1/2, moves to the right 5, and moves up 3. So we're going to start off by sketching the parent function, the original graph, the basic shape, whatever you want to call it, for y equals log base 6 of x. Now logs always look like this, where it gets asymptotic with the y-axis. And there are two key points we care about. This point is always at 1, 0, and this other point is always at the base, 1. In this case, that would be 6, 1. So now we are going to draw the new graph. Remember, we don't care about showing the axes, but I do want you to show the vertical asymptote. In this case, we're reflecting it across the x-axis, so the final graph is going to look in this shape. We have to determine where these two key points are, as well as where this axis itself would fall. Now the axis was previously at the point, or at the line, x equals 0. After it undergoes these transformations, it's going to be at the line x equals 5. The point 1, 0, reflected across the x, it's still 1, 0. Stretch it, it's still 1, 0. Then it's 5 to the right, so 6, 0, and 3 up is 6, 3. So this first point here will be at 6, 3. Then we had 6, 1, which will go to 6, negative 1, 6, negative 1/2, 11, negative 1/2, 11, 2.5. So this point over here is going to be at 11, 5 halves, which is really 2.5, and there would be the graph that we end up with. Couple things of note. Really quickly realize that horizontally there was a difference of 5 between those 2 points. Also horizontally here there's a difference of 5. It's a nice little check. And over here vertically between those 2 points there was a distance of 1. Over here, vertically speaking, there's a distance of 1/2. We did vertically stretch it by 1/2, so that would make sense. So it could be wise to look at those items just to ensure that you didn't have any silly mistakes as you went through and sketched the graph of each of those items, the original shape and then the transformed graph. One more problem that we are going to consider is on the screen right now. Perhaps you want to hit pause and try it before we continue. So in this problem, we have a quotient inside of the log, so that'll turn out to be the log of the difference. Watch out if you're doing a log like this. By the way, it's really wise to put the second set of parentheses around it. The natural log of e, it has the same base as the input. That's just going to be 1. That's one of our logarithm rules. Over here, the exponent can come out front. And I'm just going to take 1 second and rewrite this as negative 3, natural log of x plus 4, plus 1. This is our function f of x. That's the place that we want to be in order to determine what transformations we put on the original graph. In this case, we have a reflect across the x, we have a vertical stretch of 3. We're going to scoot it to the left 4 and then translate it up 1. So the original graph, or the parent function for the natural log of x, it's just that general logarithm shape that we should be familiar with. This point here is always at 1 comma 0. The other point is at the base. In this case, that's e. Remember, e is about 2.718281828, but it's an infinite decimal, non-repeating. That point is at e comma 1. When we draw the new graph, I don't need to see the axes in there, but I do need to see the vertical asymptote. Since we're reflecting across the x-axis, the end shape again is going to look in this manner. The vertical asymptote was at x equals 0. After we undergo these transformations, it's going to end up at x equals negative 4. Next, we'll look at the point 1 comma 0. It's at 1 0, 1 0, negative 3 0, and negative 3 comma 1. And the other point that we're going to look at is e comma 1. It's at e comma negative 1, e comma negative 3, e minus 4 comma negative 3, and then it goes up 1, e minus 4 comma negative 2. That should be our ending graph, but perhaps it's wise to do that quick double check. So when we do our double check here, and when we see what's happening, well, so let's start with the vertical perspective on this one. Vertically here it's 1, vertically here it's 3. We vertically stretched by 3, so that aspect is fine. Horizontally here might be a little bit more interesting to consider, but we're going to consider it. Horizontally on this graph, the difference between those 2 points is e minus 1. Horizontally here, now think about this. This is e minus 4, this is negative 3. So if we took e minus 4 and subtracted a negative 3, we would get e minus 1. So it has the same horizontal distance. We did not have a horizontal stretch. That makes us fairly confident that we did in fact sketch the correct graph. So hopefully this tutorial on working with graphing logs by hand without a calculator helps solidify the main idea. Use our property of logs to rewrite the equation, identify the transformations, sketch out the original or parent graph, and then see where the final graph ends up.